Looks like we can start. Welcome back, everyone. Kind of a small class, but these are kind of the tough classes to make during closed week. I appreciate everyone who did make it in today. If you're watching it on the recording, no worries. That makes sense sometimes. I have to admit, as a student, I didn't always make it to closed week myself each and every time. And our goal today, bringing through announcements first, is to get through the review problems, as many as possible. We may not be able to solve every single one of those review problems, but whichever ones I don't get to, I will be posting the solutions as well at the end. So not the end, but sometime probably on Friday, I'll be uploading the full solutions here. Before we get started, any questions at all so far? Okay, well, let's run through the announcements. Our goal today is just to do as many review problems as possible. And we're going to end probably around 6:05 p.m., maybe 6:10 p.m.-ish, around that time. Then we'll come here, unlock the final exam. It's really written as an assignment. The problems have been shortened up here just a little bit since we missed that review day on Tuesday. And after this is released, it's going to be due on Friday, May 9th. It says a 6 p.m. due date, but as long as it's in on Friday, it's considered on time. I just had to put a due date time on there, and 6 p.m. seemed to make the most sense. Well, the other announcements are we have several extra credit opportunities in this class. I did change this one just a few moments ago, so just this afternoon, this one got changed. And give me one moment. For this extra credit opportunity, if there's an assignment that you're struggling to get to, maybe the semester got busy, I'm going to accept them on the same day that the final exam is due. That made more sense as a final cutoff. It originally said Tuesday, May 2nd, or probably not May 2nd, probably May 6th or something along those lines. But I extended to May 9th. So if you're solving those problems that you might miss for the assignment, I mean, that's a great way to practice the course as well. I'll take those assignments for full credit as long as they're due at the same time as the final exam. So this one is an extra credit opportunity with the due date. And this is an extra credit opportunity down here that showed up on Monday, which is really kind of unusual. This is the course evaluation extra credit opportunity. And if you've done a lot of these before, you might already know that this is a firm requirement by the State Board of Education. So our math department was way behind this semester getting this thing posted. It's usually posted sometime around 14th of April. It got posted the 28th. So there's a really short turnaround on this particular extra credit opportunity. It does close out on Friday, and the math department doesn't have control on extending that. So to do this extra credit opportunity, either use the link that's available down here, or you can pop it out right here and use this link available as well and fill out the survey. Hey, says, gotcha. I did receive those files. Thank you, Hayes. So when you click on this file to fill out the survey, at the very end, there's going to be a page that just says, thank you for doing the course evaluation. If you email that page to my ISU email address, I'll mark you down for the 4% extra credit on the final exam. Just kind of substantial extra credit, but I feel like it's fair since this is a really, really short turnaround this time. Usually it was about a 2-week turnaround on doing that evaluation. It takes anywhere between 2 minutes if you're running through it to about 15 minutes if you're putting high levels of detail. And it's completely anonymized, so no worries about any kind of problems with data leaking, that kind of stuff. So those are the extra credit opportunities. The one here was the one that's been posted for quite some time. And I guess we'll turn it over to the course before jumping into the review problems. Any questions whatsoever so far? Okay, let's jump back in then. So our goal is to do as many of these problems as we can before we run out of time, and then we'll release the final exam. And this is a pretty decent document itself. If you're working on the take-home final exam, this can be a pretty nice resource for watching how to select the methods, how to implement the methods, and so on. Just as a refresher on this one is about survival after diagnosis of colorectal cancer. I'll just refer to it as this cancer. We have two particular populations that we identified. the regular aspirin use population, and the cancer-specific deaths population. And now we're going to use the chapter methods to analyze these data in total. First, let's take another look at these data. We've already said what a success is going to be, death to this particular cancer. And so now for, let's say, population, let's rather say sample one, let's count the number of successes. We usually refer to X1 as the number of successes. Let me fix my notation here. Sample one, let's refer to as being variable one, so regular aspirin use. And let's see, the study reported that out of 549 participants who regularly use aspirin, after being diagnosed with colorectal cancer, we had 81 specific deaths. So that tells us 81 successes. Always have to remind ourselves that's a morbid thing to say, but a success just means that's what the study was about. Sample size N1 was the 549 participants. So sample one was relative to variable one, and we do the same thing again. Sample two is relative to variable two, so this is same success, but for this one, these were people who did not regularly use aspirin. We're told the sample size is 730 in this one. So N2, 730, really large sample size in this problem. 141 cancer-specific deaths tells us X2 is 141. Now, from this information, we also have some statistics. P-hat1 is 81 over 549. P-hat2 is 141 over 730. And from here, we can start just analyzing this problem in full. Let me take a quick screenshot as we move down this problem. We want a confidence interval at a level 90% confidence. So this is going to dictate how the rest of the problem is going to go. It's also asking for a complete analysis. So let me write in those steps on there. On the real final exam, I do have that structure typed out just out of convenience. The state phase is us just saying, what is the practical question that actually required statistical inference? You can either cite it or just directly write in your version. Usually the question mark is kind of a dead giveaway on what the practical question is. It asked, does the data suggest regular aspirin use after diagnosis will decrease the incidence rate of colorectal cancer-specific deaths? We're going to answer it through a confidence interval. So here we'll say, does regular aspirin use reduce? You can say the proportion of, you could say the death rate, sounds a little bit more morbid, but it's still the correct thing. Let's go with death rate. Does it reduce the death rate of this cancer? So that's the problem that we're going to try to address through statistical inference. Takes us to the planning phase where if we're going to give a confidence interval, we really need to say, what is it going to estimate? The confidence interval is going to estimate P1 minus P2. And that's helpful to put down, but we now need to define what is P1, what is P2, so we can know what we're interpreting once we do this subtraction. So in the planning phase, we already have the confidence level selected for us. We're just stating what the parameters are. Let's write out, let P1 and P2 denote. You could refer to death rate if you like again, because this rate would be referring to a proportion, but just to make it seem less confusing, I'll say denote the true proportion of deaths due to this cancer. Colorectal cancer specific deaths is how they phrased it. I'll just paraphrase by saying deaths to this cancer for patients who regularly used aspirin and those that did not Let's fit in that word, respectively. Oh geez, I got a little tight. We got it in. So referring to P1 as now being the one where they did take aspirin. P2 was not aspirin use. So P1 is now being estimated by P hat 1, and likewise for P2. At this stage, we can now write out the full confidence interval. Well, maybe not quite yet there. Before we jump to that phase, let's also check the conditions, make sure everything is in line for this particular procedure. This is in the solving phase, and in the solving phase is part 1, condition checking. I'll just paraphrase that to conditions. And in the conditions, first thing we're looking for is, do we have random data? Let's read through this again. We had study participants, 730 similarly diagnosed individuals. I don't see any information on randomization, so we'll loop back to that and say our conditions may be met provided the data was random on both of those samples. Other things that we need is, well, when we're checking conditions, we have to have enough successes and enough failures. Here's the successes, 81, and the failures is going to be quite large on this problem as well. So really, we're just listing this out just to indicate we knew what the right benchmark was and that it was successes rather than, say, expected successes in a different situation. So let's say for sample 1, there was X1, which is 81 successes, and the benchmark on that has to be greater than or equal to 10. Successes, and take the sample size minus the number of successes. So 549 minus 81. We'll just use this as a calculator for the moment. 468 failures. And we want to say it's greater than or equal to 10, just as a reminder, and make that benchmark as well. Then next, taking a look into sample 2, let me see if I can fit that in. Sample 2 had X2, which is 141, greater than or equal to 10 successes, and N2 minus 141, which was sample size 730 minus 141. So 589 failures. But recall, failure is a good outcome for this particular situation for these patients, which is greater than or equal to 10 failures. So that's what we want to see. We're exceeding 10 on every single success versus failure for both samples. So to wrap up on the condition checking, pretty fast for this kind of categorical data is just to say the sample sizes are large enough. And so this is a common thing we've been saying a lot on these problems. The conditions are met. Provided both samples were random. Short for were randomly selected, really. So now with the condition checking out of the way, we can go to the next fun part and just crank out what is going to be our standard error and then the full confidence interval itself. Any questions at all, folks, so far? Okay, to get the right standard error in this problem, we just want to take a look at p hat 1, p hat 2. So that's going to be our major thing, but let's just take that whole thing as a screenshot just in case we need more. So now off to parts 2 of the solve phase, we're just going to calculate p hat 1 minus p hat 2. So this will be the direct center of our interval, which means we're directly estimating p1 minus p2. But we need to throw in the margin of error, or else this estimate is essentially useless. So we'll add and subtract a critical number z star, multiply it by the standard error of p hat 1 minus p hat 2. I'd say probably a good place to start on this is standard error. Let's compute that as a side project on the right. Standard error, p hat 1 minus p hat 2, is by definition, take the square root of, we take p hat 1 minus p hat 1, divide by sample size n1, and then p hat 2, 1 minus p hat 2, divide by sample size n2, and we get our standard error out. Let's throw in the values, get a number on this one. So back to any generic calculator will do the job for this kind of problem. Let me move it up here like that. And following the recipe we see out here on the formula, go square root. And inside that square root, let me move this over so we can see the whole thing. It's going to be 81,549. Let me put it in the numerator with the extra set of parentheses. 81,549 times 1 minus 81,549. Divide by, now just do the same sample size here, 549. That's kind of a lot, but just put it in carefully. Write some stuff down on paper or type it out just for the sake of partial credit. And then do it again on this one. So same thing with p hat 2. 141 divided by 730 times 1 minus 141 divided by 730. I was hoping to get this all in one line. Divided by 730. It's just wrapping around down to the next line here. Let me check that parenthesis, should match up with that one. And we get this as a standard error, 0.02104. I'll round this to. Let me double check the numbers. I have a tendency to copy these down in a weird way. 02104 upon rounding. Well, how's that look to folks? Does that look all right based upon that calculation? Okay, with that out of the way, next thing we might want to take a look into is what is Z star? That means we should look up the confidence. We're at 90%. And we could do a table lookup on that one, but it's just as easy to go like this. The good calculator available, just go Z star equals Q norm. 1 minus the confidence, divide by 2, and set lower dot tail false. So either just look up the table that we have in, I believe, chapter 14, chapter 19, or run this same syntax we see right over here to get it going. So I'll use Q norm. 1 minus C here is referring to the confidence level, so 0.90. Divide by 2, lower dot tail, false. And we get this value here. Hey, it looks familiar, so that's even a bonus. Let's round this to 4 places, 1.6449. So we've got our Z star down. We already had p hat 1, p hat 2. So we're just importing all in the information here and getting our confidence interval out, estimating the P1 minus P2. So here's the pretty much final steps in computing all this. In this position, I'll go 81,549 minus 141,549. Add or subtract critical number, 1.6449, and multiply it against standard error we found, 0.02104. And it's just back to the calculator with this one. But I think we're done with the summary data. So that was, there we go, that fixed it. At this point, the results we get, upper bound and lower bound, are going to bracket P1 minus P2. So now, the thing we really want to estimate has bounds. Well, with a confidence level of 90%. Let's find both of those bounds at once and then move through the problem. Any questions at all so far? Yeah,
I think the P2 was 739.
Oh, thanks for spotting that. That is an awkward number there. So 7:30, forgot the exact, or 7:30 exactly, rather. Awesome. Thank you for spotting that error there. Let me highlight that. Other questions at the moment? Okay, so with the corrected values, we're now on really good track with this. So take this whole thing, let's copy it in or type it in carefully once again. 81, 549, nice 141, 730. I'll use lower bound first, so go minus 1.6449, 0.02104. Double check those numbers. Okay, looks pretty good so far, and lower bound is negative at negative 0.08. That would be weird with one parameter. If it was just P1 and you get negative like this, standard thing to do is round to zero, but another standard thing to do is just check your values really carefully. It's possible, but it would be kind of weird. That's absolutely allowed, however, if you're taking the difference between parameters. So I'll take 4 decimal places on this, negative 0.0802. So about negative 0.8% is what P2 is exceeding. Remember, P2 was a death rate of these cancer-specific deaths not taking aspirin. Let's see what happens on the upper bound. On the upper bound, still negative. That tells us we have something statistically significant. It was positive, 0 is in the interval, but it looks like our whole interval is negative no matter what. So to 4 decimal places, negative 0.0110. And we did a couple things with this interval. Once we wrote this out, you could solve for, say, P1. You could interpret it just in this format. Whichever way you'd like to go would be totally fine. I do think it makes it easier if we solve for P1, so let me write in one more line. P1 is going to be bigger than P2 minus 0.0802. That's going to be less than P2 minus 0.0110. This stage, we're nearly there. We just need to give a conclusion based on our confidence level. And let's just make a reminder. This was 90% confidence. So for the final conclusion, what we probably want to write in is exactly what we said our parameters were. Here they are, as well as the thing we were trying to solve in the very first place. So take a look at your statement that you put on the very first step of the analysis. So we can say here for the conclusion, we want a practical conclusion that has no technical jargon that A would understand. Imagine you're a reporter just saying something on the local news, something like that, concluding what all this information says. We'll say with, or we have 90% confidence that, let's see, we call this proportion of deaths due to this cancer. So let's match that language. That I'll refer to this variable here. The proportion of deaths to this cancer for, we're referring to P1. So let's look up what P1 is referring to. P1 came first. And so we said regularly used aspirin and those that did not regularly use aspirin. So P1 is all about regular aspirin use. Proportion of deaths to this cancer for patients that regularly used aspirin is from, now we're referring to the values here, and we're going to relate it to P2, non-aspirin use. So the death rate was from about 0.8% lower to about 0.11% lower. I said here proportion rather than percent. So you could always backtrack on that if you like, or keep it as a proportion. Totally your judgment. I think percentages do work better for a practical conclusion, but I'll stick to the proportion. It is a fair way to write it. So it's from negative 0.08, let's say slightly different. It's from 0.0802 lower to 0.0110 lower. Then now we're relating it to P2, so same cancer-specific deaths, but not using aspirin regularly. So I'll say it more tersely by saying lower than these patients that did not regularly use aspirin. Let me include some space here. That's starting to look like it's running together. So that's a pretty good conclusion to give for just the confidence interval we produced. The statement was asking us, does regular aspirin reduce the death rate of this cancer? And yeah, we have lower on both ends. So we can finalize this by saying this provides significant statistical evidence that regular aspirin use reduces the death rate, which would be referring to the proportion again, but now matching up their language, the death rate for this cancer. So that's the full rundown for a problem like that one. Lots to do for these kind of problems, but I'd say the tricky thing is making sure you're using the right standard error and also making sure you're checking the right benchmark for the conditions. One way you can do these kind of problems, though, is the final exam is a take-home exam. Since really the experience with statistics there are loads and loads of different methods, but statisticians, they take their time, they do their research, and that's what we're doing. Double check that we've got the right method by just going into one of these folders. Let's just emphasize it by doing it ourselves. You could load up the document, but that's the full step-by-step solutions to all the methods. Or this is the short and sweet summary. It says here, for the large sample confidence interval, successes in the sample, failures in the sample for both samples exceed 10. There's our standard error. So it pretty much gives us the full rundown. If it was a hypothesis test, we'd just be looking into this information and we'd be using this as a standard error. Gets a little bit more involved with the pooled sample proportions. Hang on, where does it say that? Comparing two proportions. Doesn't quite put in all the information there, so be careful with this one. Looks like for that one, you really would want to open the chapter 20 for the full description. That one was a briefer summary, it looked like. Because if this was a hypothesis test problem, then we would be doing this work right here. It was missing that one definition in the document where it referred to standard error p hat. It was talking about that one. And then the formula became this for the hypothesis test. Well, let's get back to the next problem then. So one down, several more to go. This one looks like it's going to be a one sample T method. We can see that because if we're talking about newts 1 through 14, but we're dealing with, looks like the same limb on the same newt, so referring to the same individual twice, these look like they would be paired data in this kind of situation. There's a problem pretty, a problem pretty similar to this one on the real final exam. So it looks like another good one to run through. It says, biologists studying the healing of skin wounds measured the rate at which new cells closed a razor cut made in the skin of an anesthetized newt. So they put these newts through a lot in this experiment. In one experiment, the two hind limbs of 14 newts were assigned at random to either experiment or control groups. This is telling us we're dealing with an experimental design. Excuse me. And so it looks like just from this statement alone, we do have random data. Provided everything in the experimental design was done appropriately, the data is now considered random from the random assignment on the experimental versus control. Now here's what else they did in the problem. The electrical field in the experimental lens was reduced to half its natural value by applying voltage. So I guess they electrocuted them or something along those lines. It'd be interesting to see what they did. The control limb was not manipulated. So the table in 17.7, well, this table right here, gives the rates in micrometers per hour at which new cells closed a razor cut in each limb. We're looking for evidence that changing the electrical field from its natural levels slows healing. Slows is a direction, and it's a hypothesis test. So it looks like we could form this as a left tail test just by this information. At 1% means alpha is going to be set to a 0.01. So that's a setup so far. Here we can start by saying state, as we did before. Again, this structure is just provided on the exam. And I'm going to, and this time, just cite part of the problem. This is usually not worth a lot of credit on the problems, but I found that requiring this on a full analysis just makes us more accurate since we're thinking about the problem all along. If we're told to say what is the actual practical question of the problem that required analysis in the first place. Now, next thing we want to do is state the parameter. So here's the planning phase. We want a parameter and a statement of hypotheses since it's a hypothesis test. And let's define the parameter in one shot. Let's say let mu sub d, to remind us we're doing a paired t-test. We're analyzing the differences amongst the experimental and control limb. Let mu d be equal to, this is all about the healing rate in micrometers per hour. So it's going to be the healing rate difference. And let's explain further. Experimental limb with looking at this part, the electrical field reduced to half. Minus the control limb. So we're looking at the difference in healing rates to that incision that they gave. They said it was, let's see here, just to remind ourselves. A new cells close a razor cut. They didn't say too much about that. They anesthetized them, they made a cut, and then they're looking at the healing rates in micrometers per hour. And these were the control healing rates, experimental healing rates. But we're going to specifically analyze the difference. And it was asking, does changing the electrical field slow the healing? If that's true, we went to experimental minus control, and the experimental healing rate was slowed down. We expect this to be faster. So that's informing us the hypothesis test should be H naught mu d equals 0, H8 mu sub d for differences less than 0. And if you did this different, control minus experimental, and we think experimental slows the healing rate, you would have said positive here. So as long as your information is consistent, you can phrase this in a lot of different ways. We're going to do this at a significance level. Alpha is at 0.01. So we've got the statement phase, the planning phase down. Now we're going to check to see if these data even meet the conditions. So here is the solve phase coming up next. So this will be condition checking for paired data using one sample t-test. First thing we need to do is import all this data. So let's see, if we're back to this folder, just like on the final exam, there could be a document where there's some data available just for the sake of convenience, so you don't have to type these out by hand. Let's make this a little bit bigger. Sorry, messing with the windows here. Oh, geez. There we go. That should be big enough. Oh, there's supposed to be a script field. There we go. I got it to come out. So first thing, go here to import the data. I have it down here in the thumb drive under review problems. I'll just generically call it problem 4. I'll leave it as is. All the data looks like it's imported correctly. I have to scroll down on this resolution, hit import, and you should have this field right here, this tab, which I usually just close out. So here's our data, the Newt number, experimental lim, control lim. One thing to be careful with this kind of problem is if we decide to subtract in a certain way here, we do have to be consistent. So let's make sure we do experimental minus control. And I'll call this EXP. Well, let's just call it difference. That'll be a better, easier way to put this in. Difference will get the result of, call problem 4, and $ select, experimental lim first is how we state our parameter, then minus. It's kind of a long line, so I'm just going to hit enter right in problem 4 again. $, and now go to control lim. Let's run this just to make sure everything is going according to plan. It looks about right. If I get a 10 there, that's because it was taking 23 minus 13, giving us the right value 10. So it looks like consistent differences. Now we're going to do the condition checking.
I have a question about mu of the alternative hypothesis.
Yeah,
So if the question is if changing the electrical field from the natural state slows healing, wouldn't it go the other way? Wouldn't we want a positive value to prove it?
let me think about that. So slowing healing would mean the average for these data. This is always a really good question because directionalities are tricky, right? So slows healing when half the electrical field was applied means smaller average. And then it would mean for over here, for these data, we would expect a larger average because the healing rate should be higher in this situation over here. So larger average healing rate. So that's usually how I start to think about it. Which one would have the larger average? So this one is going to be smaller because we're slowing the healing. And if we go experimental minus control, we're taking the slower number minus the larger number, which should give us a negative down below right here. But does that make sense so far?
Oh, okay. I was thinking that it was like time, not
Oh, I gotcha.
getting the values.
Well, it is kind of a time because it's in micrometers per, let's see, micrometers per hour. So it's a rate involving time.
Yeah, because I was thinking that if it's longer time, the longer one minus the shorter one would give a positive value.
Oh, I see what you mean. Yeah, so slower healing means, oh, hang on, means a larger value. No, I think I did get mixed up on that. Good call on that, Summer. I think I was slower healing. If I think of this as a smaller number, that's faster healing, right? That is some awful directionality on this problem. Let me think if I can think of this a little bit better. Slower healing means larger average time to heal. Yeah, I absolutely agree with that. Do folks agree with that as well, with that revision there? That's a tricky problem. Thanks for spotting that. That means this is the wrong direction. And for slowing healing, larger average, if this has faster healing, then we are expecting a smaller average healing rate. And that means down below right here, that really does have to flip. It's got to be greater than 0. So yeah, I totally agree with you. Now, thinking of it a second time through the logic, I think we're just emphasizing if we're talking about time and slower healing, that means smaller number right here. Or hang on, larger number right here for a slower healing rate. Awful directionality in our brain for that one. Thanks for the revision on that one right there. I totally agree now after thinking about it quite a bit. Other additions or thoughts about that one so far? Okay, so now with the revised value down here, let's now check out the conditions. And if we have a positive right here, that should be shown in when we look into the condition checking phase as well. So again, thanks for stepping on the brakes on that one and getting the directionality right. That seems like an often very tricky phase for this kind of problem. Now for condition checking, we just go hist. Once I get on the home row on the keyboard, histogram of the differences. And this is kind of tricky in a way. It doesn't matter what happens for the data in the experimental limb nor the control limb, because the only thing we're analyzing is the differences. Let's make sure this comes out right. Let's change or delete the main title. Always your choice on that one. And I'll say here for the X label on the X-axis, this is going to be healing rate difference, and just a short description, experimental minus control. So running this should give us a pretty decent histogram to look at. Let me make sure it does plot. Sometimes you get an error if this window is just too small for RStudio to do anything with. And looking at this, this would be our data. Most of the data looks like it's in the negative range, a little bit in the positive range. And this is our experimental minus control. So let me export that out. Get that red dot out of there as well. So here's our data. This takes us all the way back to, say, chapter 1 or chapter 2. Looking into this data, we now need to discuss what the sample size was and how it's going to relate to any deviations from symmetry. The overall deviations for symmetry we're seeing is here. Because of, looks like one observation and another observation, we have a little bit of left skew. So we can now say the sample data or the sample differences is skewed to the left. Looks like curiously, most of the differences turned out to be negative in this problem, with about 3 positive differences in this range right here. The sample size is n equals, we can check that really fast, 14 newts were used. So we have differences skewed pretty substantially to the left due to those 2 observations. The sample size is also pretty low. So this would say probably the conditions really aren't met for this one sample t-test. These data do have some challenges that they have already together with them. So we can say here, the robustness conditions for the t-test are not met. Let's look into that further to really be sure on that. Where we would go was all the way back into the Moodle website, checking our resources. and go to chapter 17. Let's make sure we have everything we need here. Chapter 17, let's just look into one sample T procedures. And what we're looking into is these conditions here. This is the robustness conditions, deviations from normality that we see in the sample data. And we're in the first bullet point. Sample size is less than 15. It says for instruction, use T procedures if the data appear close to normal. However, if the data are skewed or outliers are present, do not use this distribution. We're looking at data that does have some obvious skew to it. We were wondering about the strength of that skew potentially, but we could also check for outliers while we're at this. Let's add a new line on this condition checking phase and do box plot, differences, and the Y label would be the same as what the X label is in the histogram. So let's just copy and paste that over. Our box plot looks kind of funny, so let's fix it, but it did reveal already that's an outlier as well by the 1.5 IQR rule of thumb, which is just a rule of thumb. But the situation is looking even worse now that even by a rule of thumb, we do see an outlier. I might have some issues here on some of the graphics, but for the sake of time, I'm just going to do that right here. Let's run with that. We can say furthermore, there is a potential outlier on the lower end. So the data was random due to the experimental design, but the robustness conditions are not met, and this is just giving us more information along that direction. It's up to you how you'd like to analyze the data from this point on. In chapter 17, we saw data that was challenging like this. You can now use a non-parametric method if you would like. But in the interest of time, let's run the t-test and then just mention all of our shortcomings once we go to the conclusion. Does that sound right to folks so far as a plan? Okay, so this was the condition checking, a little bit more messy for quantitative data versus categorical, which is curious. Now for part 2, this will be the solve phase. It was a hypothesis test, so all we really need is a test statistic and a p-value. But if we have raw data like we have here, already imported in RStudio, this is a good time to just take advantage of t.test. So here is the hypothesis test. Run t.test, pass to it just the differences. And really that's all we have to say here, or hang on. Not exactly all we have to say. We have to also recall we're doing a specific hypothesis test with a greater than direction here. So let's run alternative equals, check the way that alternatives are given. We want greater, and it has to be typed in exactly like that with the quotes and everything. So alternative equals greater gives us that right tail test. Let's make sure we copy this in by making that first thing I put in. So if you decide to analyze it this way, this is a decent way to give it a try. You can take a look into the syntax again. And also just another reminder, if anything kind of goes wrong with the syntax, you can just copy paste this, send it to my email, and I'll be very happy to work with it with you. So hit Control A, Control Enter, and here's our results from the test. P-value is gigantic, and the test statistic came out at -2. Something seems a little bit awry with this. -2 standard deviations for test statistic T should suggest a smaller p-value than that. Starting to wonder on our condition again on our hypothesis test. We went experimental minus control. Experimental minus control here. We did the right tail test. Starting to wonder if this is a left tail test. For some reason I'm going a little in loops on this one. I'm going to blame this on insomnia. But I think it might have been a left tail test. Let's see if we can make a small change here, because usually 2 standard deviations really does mean a smaller p-value. Plus, we're also looking into data that's showing the observations, say, not quite there, on the box plot are telling us they are mostly negative if we're going from this quartile down, that's the 75th percentile. About 75% of our data actually is negative in the first place. This is kind of weird. Let me put here less. Now the p-value seems about right for 2 standard deviations and a little bit over. The p-value is now at 0.03202. Let's see if we can resolve this logic here. Anyone see what is going awry potentially with the greater than versus the description here? Changing the electrical field from its natural levels, they're talking about control limb, into the experimental limb, slows healing.
I think I might have figured it out.
Yeah,
The
go ahead.
micrometers per hours is the rate at which the new cells are formed. So maybe the higher number is the rate it's being closed, like the new cells being formed.
Potentially, yeah. So that might be the case. I might have to come back here to give just a little bit more thought on this one. For some reason, my brain is kind of going blank. But it seems like this one has a pretty healthy debate on it. I'm going to try to write questions. Well, I already wrote them. I tried to write questions that are a lot more cut and dry than this one. That's easy to get into. But I think this one might be less than. I'm going to come back to these notes, clean them up a little bit more, and maybe give more description on a definitive direction for this one. But hey, that makes it a fun problem if it's kind of challenging to really discern the actual direction based on the wording on this. So coming down below here, second issue is maybe the wording is wrong. Potentially, I might have just typed it up in a funny way. This could be all my fault on just the way the wording was put into the problem in the very first place. But the giveaway that there's something awry is that's pretty significant for a one-tailed test at 2 standard deviations. And so this does look like it's going to be the right analysis. Let's throw this into the problem. We have a test statistic at negative 2.0239, p-value at 0.03202, but we have alpha at 0.01. So this is greater than 0.01 set to alpha for our hypotheses. That means no matter what we do, left tail test or right tail test in the syntax, we are not going to reject the null hypothesis. So that's kind of comforting in a way, but not a good way to solve every single problem, obviously. So I'll come back to this and clean it up a little bit. Let's now give an overall conclusion to this problem right here. So here's our conclusion. I'm just putting this down as a temporary screenshot. With our failure to reject due to a large p-value and the fact that alpha is at 0.01, we might conclude by saying something along the lines, the sample data, or hang on, let me say this in a slightly different way. We failed to provide significant statistical evidence that, now let's read out this part right here, the difference in the healing rates experimental limb minus the control limb is. Now, here's where our conclusion is going to struggle. We do have to pick a direction in our conclusion. So we might say is, let's go with negative just to match up with the final syntax or output that we took here in t-tot test. So say is negative when the electrical field maybe before even that. Don't forget that this is all about averages. And the way it's being written, it sounds like we're just talking about the individual newts. But the individual newts experiences did vary. Some of them had positive differences, some of them had negative differences. So we should say is negative on average to emphasize we're talking about a population mean, a parameter. When the electrical field is reduced in half. So kind of a strange problem, kind of interesting debate on that one as well. Thanks for thinking about it with me and deciding which way it could be. But any last questions or comments about this one? Okay, well, for the interest of time, for our next problems, let's take a look at the kind of problems that we have. We'll categorize them to say what statistical method we might use. And then that's going to take us to about 4 or 10 minutes away to when we're going to release the final exam as the last assignment. Excuse me. Hopefully the voice holds out until then. Not sure why I saved it. Must be a reflex. So next problem down the line. This is the one problem on the exam where I'm going to directly tell you, use these methods right here. So this is the one on road rage. It doesn't look like we had time to get to it, but if you're interested in this problem, I will put down the analysis and you can see how that goes to adapt it to your current problem for the chi-squared methods. Next problem number 6 is asking for a complete analysis using a hypothesis test. I'm reading through this problem where we're wanting to decide is the data categorical or quantitative. Can anyone spot the difference on these data? Yeah, go ahead.
I think it's quantitative because it's reporting in percentages. It could be categorical, but I think it's more likely quantitative because it's reporting percentages. It's not really discussing any proportions, since they're, yeah.
Well, usually the percentages itself could be rewritten as a proportion as, say, a 0.136. So sometimes actually the percentages as well usually indicate it could be categorical for these kind of problems. For quantitative, we would want to find the unit. Is it a heel rate, like say micrometers per hour, or is it a time, a distance, or anything like that? But if it is categorical, we have to say, what would the categories even be on this one? So let's take a look at this again. The Substance Abuse Mental Health Services Administration conducts a survey on drug use by type of drug and age group. They tell us results are published here, so I guess you can look that up at any time you like. And according to that publication, 13.6%, or a proportion of 0.136, of 18 to 25 users, 25-year-olds, were current users of marijuana or hashish in the year 2000, however you pronounce that. So that's interesting information, but that might actually be successes versus failures, where success would be the current users and a failure would be non-users of that category of drug or drugs. It says next, a recent poll of 1283 randomly selected 18 to 25-year-olds revealed 205 currently use marijuana or hashish. So that sounds like we're talking about successes versus failures, and these would be the successes. So from that, looks like we really are looking into categorical data. We have outcomes exactly 2, successes would be regular users. Failures would be non-users of those substances there. And we want was there multiple populations? But they're only talking about specifically one kind of population, the people in the age range of 18 to 25-year-olds. So this would be a kind of problem due to being categorical, due to being exactly two different kinds of outcomes. Looks like this would be the one sample proportion methods, which would then direct us to chapter, let's think about that. I believe it was chapter 19. It's been a while. Chapter 20 was the two proportion methods. 21 was the chi-squared methods. So this one's kind of tricky to really track down because giving as percentages is not necessarily saying what we're looking into. I feel like this paragraph right here is what really narrows it down. This information was useful for the hypothesis test. This is going to turn into the value P naught using the null and alternative. But this information really broke it down that out of the 1283 randomly selected 18 to 25-year-olds, we're categorizing them 205 in one group, the remainder in another group that we call failures. So that's the rundown on problem number 6. Any questions on that one? Okay, then down the line onto the next one. This one, I had to make a change. We lost a whole entire review day, which was unfortunate on Tuesday. So I felt like making the exam at the same exact length with this problem, which was pretty challenging on exam 2, was just a little bit too much. So what I decided to do with this problem, this is the power analysis problem, is just to convert it into an extra credit question. The extra credit is going to be substantial enough so that it's like a full-on problem swap. There's one problem on the final exam that you either are just not sure how it goes or maybe just don't like it and you prefer this problem, you can exchange it and just do problem number 7. And if you do all problems, that'd be fine as well. Your exam score can't exceed 100%. You're just putting in even more effort on that exam. But I decided the exam should be a little bit shorter, and this is one of the ways I made it shorter. The power analysis problem is now optional for extra credit. And that takes us to the last problem of the list here. Let's take a look at what's going on with this one. It says, a study examines chocolate's effects on blood vessel function in healthy people. I'd want to be a part of that study. That sounds interesting already. In the randomized, double-blind, placebo-controlled study, so we're getting random data. It looks like a pretty nice experimental design. 11 people received 46 grams of dark chocolate, which is naturally flavonoid rich, every day for 2 weeks, while a control group of 10 people received a placebo consisting of dark chocolate with low flavonoid content, probably like Easter candy, something like that. Participants had their vascular health measured, defined by means of flow mediated dilation. Not exactly sure what that is, but that's how they're going to judge their vascular health before and after the 2-week study. So some people were given really nice chocolate, other people were given just random, not so great chocolate. And then they looked into the increased over the 2-week period was measured. Increased, that would be increase of what? Cardiovascular health, with large numbers indicating greater cardiovascular health. Now they say the group getting the good dark chocolate had a mean increase of 1.3 with a standard deviation of 2.32. But right there, if we're talking about means and standard deviations, it's got to be quantitative, right? So these data are quantitative. But there's more to that to this. It's not going to be one sample because we split people into 2 populations, the so-called good flavonoid-rich chocolate and the low-quality chocolate. No one knew what they were getting since it was controlled with a placebo. We can say here, there's 2 populations. The control group, as well as the experimental group. So this would mean we're using the chapter 18 to sample mean methods for this particular problem. Does that make sense to folks for this one? Awesome. Yeah, anytime you see stuff like this, standard deviation or sample mean, again, that's almost a complete giveaway. It's got to be quantitative data. And this would be the end of the sample exam. Sorry we didn't get to solve a lot of problems on this. I think we got to close to half, but not quite there. But this is a good point to pause here, turn around, and now open up the final exam and give it a short discussion. Any questions whatsoever first before we turn over to the last project? Okay, I've got this saved up. And I'll go through this document starting on Friday, putting in the more complete solutions and that kind of thing, fixing some of my penmanship that looks like a little bit like scribbles, I think. But now we're finally at the end of the course. It was a 15-week course, not exactly a 16-week semester. It's just the finals week forms the 16th week. And for this exam here, it's just like a homework assignment, like we mentioned in class. Homework was the major part of the course. It's 40%. And the final exam itself through the syllabus is worth 15%. So it's not meant to be a major make or break you on this course. Just a way for you to do one last project, run through these problems, run through these methods, see how they compare, how they differ, those kinds of things. So final exam looks like an ordinary assignment. It has a Word document versus a PDF, and one problem with the data that you might import to RStudio if you prefer. That means you can turn it in as a regular assignment as well. I'll accept it by email. I will be on campus on Friday giving a final exam, so I can be available as well. If you want to turn in a hard copy, just send me an email and I'll make sure to be available. And one other thing, keep in mind as well, the final exam is worth 15%, but for this extra credit opportunity, if you're a few assignments behind in the course, the homework in this course is worth 40%. So depending on where you're at, that might be the better place to start. Begin with the homework. Yeah, it's going to prepare you for running through the final exam. Then get to the final exam, and it'll be due on Friday, May 9th. And here's what it looks like. Looks like a regular exam like you've been given, except it's just has some reminders that this is now a take-home exam. So for this exam, the purpose is to determine your individual understanding, so we have to work on it alone. But you're expected to be using R on this, like your homework assignments. If anything happens with your syntax, don't hesitate to email. That's one thing I can definitely help out with, just like with the rest of the course. It is open notes, open book, and if you're looking up statistical resources from other places, maybe other textbooks, you're welcome to. Just be sure you cite them on your document. Then aside from that, here's what it looks like. The problems were randomized, but it has been shortened up. So problem 1 gives you some information here. And let me go back here, make a really quick edit. I'm going to need to fix that. That should have said problem 1. Let me just make that a reminder for me. I forgot that I randomized the problems, but then I didn't change the title of that text document there. So that was an omission. Rename problem 2 to problem 1. Okay, I'll get that fixed in as soon as possible. Then aside from that, problem 2, just going to be a problem with summarized data. Problem 3, hard to tell exactly what's going on here, but look at the review problems. You should be able to match this up with a certain situation. Then big description here on problem 4. Problem 5 has a complete analysis with the structure thrown in as well. And then problem 6 looks like probably another potential central limit theorem type of problem. Problem 7 is where we're told use specifically the chi-squared methods. So this is the last problem, official problem of the exam. That's going to be a kind of fun one where we're going to decide if there is evidence that Spam, dog food, pork liver, pate, and liverwurst will be equally likely as chosen as dog food. So this is kind of a fun problem as well, using chi-squared methods. And finally, problem 8. This is the one that is for extra credit. Give it a crack. I'm going to give partial credit, so you don't have to solve all of it if you just run out of time or prefer not to. But any effort you give here can now be worth extra credit as well. So all the problems are normalized to 10 points for a total of 7 points altogether, 70 points altogether. Well, any questions at all, folks, on the final exam before we call it a day? Okay, if anything comes up while you're solving the final exam, don't hesitate to email. I can't ask a lot of questions, but if I can clarify the instructions or if the language is just kind of weird on a problem, those are questions I can address. And always anything going weird on RStudio, I'll be very happy to help out with. So it's meant to be kind of a short project, not anything too intense. With all the experience you've had so far, you probably won't take too long on this one, but it's a good one to start sooner. Maybe categorize the problems first on what methods you think might work, and then go from there. Yeah, that would be a great way to go at it, Hayes. Hayes asked about, after doing the final exam, is copying and pasting stuff like the RStudio output valid from the homework? And I'd say absolutely. The same way you've been doing the homework assignments all along qualifies for the final exam as well. So if your homework assignments have been working out just fine, do it the same way down here and you'll be in great shape. Any other questions at the moment? Okay, well, have a great weekend, folks. If you're working over the weekend, don't hesitate to email, or at any point up to May 9th, I'll be happy to work with you. But try not to work too hard, and I'll see you all later. Yep, take care. Oh, and if I have your exam, it's down here. Yeah.
Have an excellent summer.
Thanks, you too.
Yeah.
It's been great working with you.
Yeah, you as well. I learned a lot.
Awesome, glad to hear that. You too.
I think you were right that first time with that review problem.
I got you. With the less than versus greater than direction.
Yeah.
I'm still kind of vague in my mind because what you said made a lot of sense to me. So you have to somehow untangle that and take a closer look at it. Maybe after getting a little more sleep would help.
Well, I was looking at it and it's the rate at which the new cells close the cut.
Yeah.
So more cells that there are, the more the cut's healing. So the greater the number, the more the cut's closed.
Oh, yeah. I'm starting to see it that way too now. I wasn't focusing on that. I was still focusing on the time element of it, like you were mentioning.
Yeah,
But
that's
yeah,
what I first thought. But
Number
then
of cells. Yeah.
when you went back to it and was like rereading it for the third or fourth time,
Mhm.
I finally saw that part. And then I was
Got
like, oh, you were right the first time. I think. Maybe.
Yeah, I mean, that's a good experience for these kind of problems. Whenever you're doing differences in directionalities, right tail versus left tail, I'm glad that that happened on the exam because that's the kind of thought process you have to have. Think about it once, twice, 3 times, just to be sure, really.
This right tail versus left tail has been getting me all semester.
Yeah, but we're nearly done.
Yep. Well, thank you.
You
Have
bet.
a
Thanks
great
for all the hard work. You too.